And welcome, everyone. Happy, beautiful sunny day. It is gorgeous outside. Make sure you get outside for a walk today. It is so beautiful. If you wrote the makeup test, your reflection is due today. If you wrote the regular test, yours was due last week. We have some extra options for some support. So in addition to our resource room that's offered many days a week, either in person or online, we also have the PAL Center, the Peer Assisted Learning Center at Western. And they're opening Chem 1302B specific sessions for us leading to the end of the term. Check out the OWL announcement posted today to find the time and links for those sessions. I also wanted to thank you for cooperating with the technology. Sometimes technology doesn't work the way we want, so thank you for being patient last class. I have been informed that this microphone is also broken. It's working right now. We have someone coming to check on it, but we're going to do the best we can. Thank you for your patience as we move along. We have started into chapter 4, looking at redox reactions, looking at something being reduced, something being oxidized. If this can happen spontaneously, we can cause the flow of current to happen if we design this strategically. In order to be able to design a battery or to figure out if a redox reaction is spontaneous, we need to be able to assign oxidation numbers so that we can figure out what's happening, what's being oxidized, what's being reduced. We then need to be able to balance these equations to make sure that we have the right amount of reactant or the right amount of product to make that battery last as long as we want it to, or to be able to produce the amount of products that we want to through electrolysis. This starts with the basic understanding of assigning oxidation numbers. This should be a review from something that you've already done, but I think it's helpful to recap these important rules because this is the foundation to be able to do everything else that we want to do in this unit. We're going to talk about some priority rules, starting at number 1 and working our way down. When you assign oxidation states, you need to start at number 1 and work your way down. Number 1 rule trumps rule number 2, which trumps rule number 3. Number 1, a pure element is 0. Its oxidation number is 0. So if I have hydrogen gas just bound to itself, that would be a pure element. Its oxidation number is 0. If I have some solid aluminum just sitting there by itself, a whole bunch of solid, its oxidation number is 0. That's as simple as it gets. From there, we need to figure out how to assign oxidation numbers in compounds. And again, we need to assign this in priority, where A trumps rule D. Fluorine is going to be -1. So if we had sodium fluoride, fluoride is going to have an oxidation number of -1. Now, you need to know these oxidation numbers. I hate memorizing things. Does anyone else hate memorizing things? Oh, just a couple people. Okay. So I gave you fair warning. The lapel is now dead. This apparently dies in a couple minutes too, but we'll see how far we get. Okay. If you don't want to have to devote quite as much energy to memorizing, you can look at your periodic table and use this for helpful advice. Fluorine is 1 spot away from a noble gas electron configuration. If it gains 1 electron, it would have a noble gas electron configuration. Thank you. So give me 1 second. The lapel just cut out. It worked for a few minutes, but then it just crackled and died. Okay. The instructor said this worked for a while and then it crackled and died. So I'll give it a shot. Thank you. Okay, so fluorine is -1. Then group 1 metals, our alkali metals, such as sodium and potassium, get a +1 oxidation state. Yeah. Okay. How do we remember that? Well, sodium, an alkali metal in group 1, If it loses one electron, it would have a noble gas electron configuration. So sodium +1, any alkali metal. Then we go to group 2, the alkaline earth metals. They will typically have a +2 oxidation state. How can we remember that? Well, they're in group 2. If they lose 2 electrons, they'll have a noble gas electron configuration. Then we get to hydrogen. Hydrogen is typically +1. As long as we assign the rules in order, you'll always get the oxidation state of hydrogen correct. So if it's in something simple like H2O, hydrogen would have a +1 oxidation number. Most of the time, that's what it would be. But if it was something like lithium hydride, this is a unique case. But we see that lithium falls in group 1. Lithium applies to rule B. So lithium would be assigned a +1 oxidation number. The sum of the oxidation numbers for the whole compound Thank you. Thanks very much. Okay, thank you for your cooperation. We're going to get through this, and we have this one working, so that is awesome. So lithium hydride. This is a unique exception for hydrogen, but we don't have to memorize it. We just simply apply the rules. If lithium must have a +1 oxidation number before we assign the oxidation number of hydrogen, and the sum of the oxidation states of all the species in the compound must sum to 0 for a neutral compound, well, hydrogen must be -1. So that's how we figure out that exception. Otherwise, hydrogen is +1. Oxygen is usually -2. In water here, oxygen would have an oxidation state of -2. The last rule in this sequence is that our halogens are usually -1. Fluorine is a halogen. It's already been assigned a -1 oxidation state. So now we're talking about chlorine, bromine, and iodine. So if we had sodium chloride, for example, chlorine is going to be -1. So nice and direct. Those are the first 2 rules. The next rules are nice and straightforward. The next one is that if you have a charge on an ion, well, that charge is also going to be its oxidation number. So if we had a silver plus cation, well, its oxidation number is +1. Iron 2+, that charge is also going to be its oxidation number. Oxidation numbers don't mean that we have a full plus or negative charge. Here, they're equivalent to each other, but in water, H2O, that doesn't mean that oxygen has a full -2 charge and hydrogen has a full +1 charge. That would be inaccurate. Oxidation numbers are simply, jump away. Oxidation numbers are simply an accounting method, a tabulation method to be able to assign electrons. It doesn't tell us full charges, but it does allow us to keep track of what's happening in a reaction. So that's rule number 3. Rule number 4, the sum of a neutral species must be 0. Let's do that example of sodium chloride again. Sodium is going to have an oxidation number of +1 because it's an alkali metal. Chlorine, -1, because it's a halogen. We usually assign according to our rules, and then we solve for the last piece. So I would actually solve for chlorine. The sum of the oxidation numbers of sodium plus 1 chlorine must equal 0. If sodium is +1, we can solve for chlorine. Therefore, chlorine must be -1. The final rule is that if we're looking at a polyatomic ion, a bunch of atoms covalently bonded together with an overall charge, the sum of the oxidation numbers in that polyatomic ion must sum to the charge on that polyatomic ion. For example, if we had, well, actually, we'll jump to, we'll do this one. Nitrate, NO3 negative. The sum of the oxidation number of nitrogen plus 3 times the oxidation number of oxygen would equal -1. We'll just put oxygen in there. So let's have some practice assigning oxidation numbers. What is the oxidation number of phosphorus in sodium phosphate? That's what we're going to start with. Well, I can see I have a variety of atoms in this compound, and I'm going to apply the rules in order. I need to figure out the oxidation number of sodium, oxygen, and phosphorus. Well, according to rule 2b, alkali metals have a +1 oxidation number. So therefore, sodium must be +1. Oxygen, according to rule 4, well, that has to be -2. Phosphorus, well, I don't have a rule for phosphorus. I'm going to have to look at the charge of the entire compound, which is neutral, and solve for phosphorus. So in this compound, I have 3 sodium atoms, 1 phosphorus atom, and 4 oxygen atoms, and that needs to sum to 0. Well, I know sodium is +1. I'm going to solve for phosphorus, and oxygen is -2. Turns into a simple math problem. Isolate for phosphorus, therefore, phosphorus must be +5. 4 times -2 is -8, +3 is -5. Move that -5 to the other side of the equal sign, we get +5. Now, there's one other way to analyze the oxidation number of phosphorus, and this is where we'll do our polyatomic ion example. Sodium phosphate, when it dissolves in water, will produce sodium cations and the phosphate polyatomic anion. And the charge on this polyatomic anion is -3. I could solve for the oxidation number of phosphorus by solving this polyatomic anion. That would be phosphorus plus 4 oxygen atoms, and it must sum to -3. Well, 4 times -2 for oxygen gives me -8. Add that to the other side. Hooray, it's the same number, +5. So now it's your turn. What is the oxidation state of chromium in this polyatomic anion? Go ahead and chat with the person beside you, and then we'll load this question. Okay, we have our wired internet. We have one microphone working. We're in good standing. 10 more seconds to get your answer in. And 3, 2, and 1. Okay, most people went for E, and E is the correct answer, +6. We had some votes for C. C is the number for 2 chromiums, but when we ask the oxidation number of an element, we're asking for 1. That +12 is contributed by 2 chromiums. We divide it by 2, therefore the oxidation number is +6. Well done. So that's a super basic technique that we need to be able to do. We need to assign oxidation numbers so that we can do other interesting things, like analyze a redox reaction. So, as the name implies, redox means that something is being reduced and something is being oxidized. Let's look at what those terms mean and identify in a reaction what's being oxidized, what's being reduced. So now, assigning oxidation numbers is kind of old news. That's great. Don't interrupt my class, though. So aluminum is going from an oxidation number of 0 to +3. The charge is also the oxidation number. Copper 2+ is going from +2 down to 0. So I like to think of oxidation numbers like a thermometer scale. If we are going, let's talk about copper, +2 down to 0, that means the oxidation number has been reduced. It's gone down on that temperature scale. Therefore, copper is reduced. Well, that means aluminum, it's going from 0 to +3. That oxidation number is increasing. It is being oxidized. A handy way to remember which is oxidizing and which is reducing, oxidation is losing electrons, while reduction is gaining electrons. And you can remember that with the acronym OIL-RIG. Okay, so if something is being reduced, its oxidation number is being reduced, it's going down. How does that oxidation number go down? Well, it's because it's taking on electrons. So the balance of positive and negative means that it goes down. So let's analyze this problem. In this reaction, identify the oxidizing agents and the reducing agents. Well, we can now see how we can identify what's being oxidized and what's being reduced. Here, again, copper, it's going from +2 down to 0. That's reduction. Meanwhile, zinc is going from 0 up to +2. That's oxidation. We need to be able to assign oxidation and reduction like the back of our hand so that we can go on to do more interesting things. Well, this question isn't just asking what's being oxidized and what's being reduced. We want to know the oxidizing agent and the reducing agent. This is the secret agent that causes that thing to happen. Here, copper 2+ is being reduced. That means it's allowing or causing zinc to be oxidized. Copper is being reduced. It's taking on electrons. It's stealing electrons. That means that it's allowing zinc to be oxidized. So copper is the oxidizing agent. Zinc is being oxidized. That means it's causing something else to be reduced. Because it's being oxidized, it is the reducing agent. So remember that these terms are kind of opposite. It's the secret agent that allows that action to happen. Okay, so we can assign oxidation numbers to elements, to compounds, to ions. What about organic molecules? We have one more type of analysis to do if we want to assign oxidation numbers within an organic molecule. Here we have to dig back to the concept of electronegativity. So this might be 1301A or grade 11 and 12 high school. You would have also talked about electronegativity. And we have an electronegativity trend on our periodic table. As we go up, atoms become more electronegative. They hog the electrons in a covalent bond. As we go across the periodic table, atoms become more electronegative. They hold on to and grab that extra electron density. They're electron hogs. So for assigning oxidation states to carbon, we need to think about and analyze what it's attached to. Is it attached to an atom that's a bigger hog than it is? Is it attached to a more electronegative atom or a less electronegative atom? In part A, carbon is bound, has a single bond to hydrogen. Carbon is more electronegative than hydrogen. Hydrogen is less electronegative. Therefore, carbon would be assigned a -1 oxidation number. Now, this does not mean that carbon has a full negative charge. We know that this is actually neutral. But for our tabulation accounting method of electrons, we're going to say carbon has a -1 oxidation number because of that bond with hydrogen. Now, we know carbon usually has 4 bonds, 4 single bonds, 2 double bonds, some combination to give it a bond order of 4. So this is just because of the 1 bond with hydrogen. We're going to have to analyze all the bonds to each carbon to figure out what the oxidation number is. Well, if carbon is bound to a more electronegative atom, like fluorine, fluorine hogs those electrons. Therefore, carbon is assigned a +1 oxidation number. Now, again, in reality, we know that fluorine is ever so slightly negative and carbon is ever so slightly positive. But for oxidation numbers, it gets a full +1. So let's look at this example here. We want to determine the oxidation state of each carbon in the following molecule. Now, to do this, I find it's really helpful to draw out all the bonds. We should know how to interpret this structure. What functional group do you see here? Does anyone want to say what functional group they see into the microphone? What functional group is that? Anyone want to put up their hand and tell us? What is this one?
Carboxylic.
Carboxylic acid, that is correct. We have a carboxylic acid, a carbon with a double bond to oxygen, with a single bond to the hydroxyl group. That makes a carboxylic acid. Every bend or end of the line is a carbon atom. It's implied, but because we're scientists, we know how to read this structure. We also know that carbon needs a filled octet. It needs a total of 4 bonds. That could be 4 single bonds, 2 double bonds, any combination to give it 4. In organic chemistry, we don't draw in the hydrogen atoms because it gets really monotonous and boring. But as good scientists, we know that those hydrogen atoms are there. So the first step is to draw in those implied hydrogens so that we can then analyze the oxidation numbers. So let's start with the carbon over here. I'm going to analyze each of those bonds to carbon and tabulate the overall oxidation number for this first carbon. Well, I can see that this carbon has 3 carbon-hydrogen bonds. Hydrogen is less electronegative, so for each of those bonds, carbon is going to get a -1 oxidation number. Carbon has one carbon-carbon bond. This is assigned an oxidation number of 0. 2 identical atoms share the electrons equally. So neither gets a plus or a negative oxidation number. It's simply a 0. So 3 times -1 gives me a -3 oxidation number for this first carbon. Let's do this next carbon. Similar pattern. This time we have 2 carbon-hydrogen bonds. Hydrogen is less electronegative than carbon, so we get a -1 oxidation number for each of those bonds. Then we have 2 carbon-carbon bonds. Again, the same atom means that neither gets more electrons. That sums to 0. 2 times -1 plus 0 gives us -2. Then we can analyze the oxidation number of the last carbon. And this one's a little bit more interesting. Here we have a double bond to oxygen and a single bond to oxygen. The single bond has a bond order of 1. The double bond has a bond order of 2. I'm going to simply add up the number of bonds to oxygen, but I'm going to count that double bond as 2. So I have 2 plus 1 bonds of carbon to oxygen. That means 3 total bonds to this more electronegative atom. That means the oxygen gets the -1, which means carbon gets a +1 oxidation number for each of the bond orders to oxygen. Then I have 1 carbon-carbon bond. I can add those together. Therefore, this carbon atom must have an oxidation number of +3. So we can assign oxidation numbers in elements, in compounds, in ions, and now in organic molecules. We want to be able to assign these oxidation numbers so that we can interpret a redox reaction where something is reduced and something is oxidized. Now, if we want to design a really cool battery and be able to come up with something cool for your new phone, we also need to know how to balance these equations. Now, put up your hand if you enjoy balancing redox equations. Okay, most people don't, and if you do, that is awesome. I don't mind balancing them either, but it can be a tedious process. Who remembers balancing redox equations in high school? Okay, I see many hands, but not all the hands that should have gone up for balancing redox equations. You may have memories of frustration. You may have memories of working on the problem and realizing it didn't balance out and crumpling it up and throwing it across the room. You may have some of those memories, but hopefully after today's class, you can have more positive experiences. My one piece of advice I have a couple pieces of advice. One is if you get stuck, and if you start this cyclical process of this doesn't balance, this doesn't balance, this doesn't balance, start with a fresh piece of paper. Odds are you miswrote one tiny sign or one tiny number that's scrambling this process. Start fresh and you'll probably be fine. Balancing redox equations is a little bit more involved than a typical balancing of an equation. Usually we can balance by inspection. 2 carbons here, add a 2 in front of this carbon. 3 carbons here, 3 carbons here. But for redox reactions, inspection or by inspection doesn't always work. Sometimes species that we need, like water or H+ or OH negative, aren't yet written in. And it can be challenging to know how to add those species into our balanced equation so that we have an overall balanced equation. So we have a robust method for balancing equations. It looks like a lot of steps. So I'm happy to tell you that step number 1 is make sure that you have a redox equation. If you don't do this. This is way more involved than necessary if you don't have to. So step 1 is figure out if you have a redox equation. How do we figure out if we have a redox equation? Well, something needs to be oxidized and something else must be reduced. We can't just have one. That wouldn't actually function and happen. It would be a half reaction. So first, we want to make sure that the oxidation numbers are changing. Step number 2 is to split the redox equation into two halves. We want to have one half equation that's being oxidized, one half equation that's being reduced. Then we're going to balance each of these half equations separately and then combine them at the end to have a beautiful balanced equation. So once we've separated our two half equations, sometimes it can be a little challenging to know how to separate them. This is when assigning those oxidation numbers is helpful, because we'll have the oxidation half and we'll have the reduction half, whatever species are needed to make those two pieces. Or you can combine interesting pieces. So if you have manganese, well, you want the manganese species together. And if you have iron, well, you want the iron atoms together. That's also a handy way. So we now have two half equations, and this is a really helpful strategy. You may have another strategy that works. And if you have another strategy that you prefer and it always works, then you're more than welcome to do that strategy. There are at least 2 or 3 main ways for doing this. This is robust. It takes a little bit of time, but this method always works. So once we have these two half reactions, balance everything that's interesting. Basically, all the atoms by inspection, 2 iron atoms, 2 iron atoms, 3 manganese, add a coefficient 3. Everything except hydrogen and oxygen. Those ones are a little bit more complex. Then we want to balance the oxygen. Now we can't just add O2, because in solution, we don't have a lot of O2. We can't just add atomic oxygen, O, because we don't have that in sufficient concentration either. Maybe up in the stratosphere, we might have some atomic oxygen, but not enough meaningful oxygen down here. If we want to add oxygen, we have to add oxygen by adding it in the form of H2O. The reactions that we're going to balance, most of them, happen in aqueous solution. So there's always lots of water around. Or if we're doing a reaction that doesn't happen in aqueous solution, well, then you don't need to worry about adding water. So we balance the O by adding H2O. Then we need to balance the hydrogen atoms. A way to remember to balance O before H, when you balance O by adding water, you're also adding hydrogen. So if you've already balanced the hydrogen and then you add water to balance the O, well, you've just screwed up your oxygen balancing. So start with oxygen, then to hydrogen. And now we need to pay attention. Is the solution acidic or is the solution basic? If the solution is acidic, that means we have extra H+ ions floating around, and we can simply add H+ to the side of the reaction where we want more hydrogens. But if the solution is basic, we don't have a meaningful amount of H+ ions swimming around. So we can write it on paper, but in reality, there's not enough of it there to meaningfully react. So instead, what we need to do for basic reactions is to add H2O to the side that we really wanted to write H+ to. But then really quickly, before we forget, we add hydroxide to the other side of the equation. So water where we want the H+, and then very quickly to the other side of the equation, we add hydroxide. In effect, we're subtracting the hydroxide. H2O subtract hydroxide is H+. The net effect is that we've added H+. Another way of thinking about that is adding H2O to one side and then subtracting most of water but leaving the proton on the other side. So this is how we balance in a basic reaction. Next up, balance the charges. We can't remove negative charge. We can only ever add negative charge. We can't remove positive charge. We can only add electrons. So we add electrons to whichever side we need to make more negative so that both of the halves of the reaction are balanced. Then we bring them back together. We need the number of electrons being produced in one half reaction to equal the number of electrons being used up in the other half reaction. We can't have a balanced redox reaction if we're producing more electrons than we're using up. So we need to find a common factor for the electrons to balance. Then we bring them back together, cancel out common terms, and then we check. We can always know that we've done it correctly because it will balance. So let's go ahead and balance this first equation. So step number 1, let's make sure we're not wasting our time. Let's assign oxidation numbers here. Oxygen is going to have an oxidation number of -2. There's 4 oxygens there. That brings me to -8. The overall charge on this ion is -1. So I need to get from -8 up to -1, and that oxidation change comes from the presence of manganese. Therefore, manganese must have an oxidation number of +7. Well, manganese is going from +7 to +2. That means it's being reduced. In the other part of the equation, again, I see an oxygen with a -2 oxidation number. There's 4 of them, so that takes me to -8. Then I need to get up to -2, so I need +6, but there's 2 carbons to get me there. That gives me a +3 oxidation number. Now, I just did a lot of talking, and if you followed along, that's great. If not, write it out so that you can be 100% confident to be able to calculate that oxidation number. So you can turn it into a mathematical equation. Well, what's the oxidation number of carbon in carbon dioxide? We have 2 oxygens, each with a -2 oxidation number. The overall charge is 0. Therefore, carbon must be +4. That means carbon is going from +3 to +4. It is being oxidized. So step 1, do we have a redox reaction? Yes, we do. Something's being oxidized, something's being reduced. I'm going to take the reduction half reaction and put it on one side, and the oxidation half reaction and put it on the other. So we always want to double check our work, and you can double check my work too, because we don't want to miss writing any positive or negative signs. So we've split it into the 2 half reactions. So that step is done. Now we're going to balance everything that is not oxygen and hydrogen. So I'm going to start with my reduction half reaction. 1 manganese on the left, 1 manganese on the right. It's already balanced. Don't mess with a good thing. Over to the oxidation half reaction. 2 carbons on the left, 1 carbon on the right. I can't make one less, but I can make the other one bigger. So I'm going to add a 2. I just said you can't make it less. I'm going to take that back. You can certainly balance with halves and fractions, but just don't for redox, okay? Okay, so we've balanced all the other atoms besides oxygen and hydrogen. The next step, balancing the oxygen. On the left, for my reduction half, I have 4 oxygens. On the right, I have none. I need to add oxygen in the form of water. I want to add 4 oxygen atoms, but I can't just add O because it doesn't exist in this experiment. It does exist in the form of H2O. So now, just paying attention to the oxygens, 4 oxygens on the left, 4 oxygens on the right, it is balanced. Going to my oxidation half reaction. 4 oxygens on the reactants, 2 times 2, which is 4 oxygens in my products, that is also balanced. So then we go to our hydrogens. And we go back up top and say, well, is this acidic or is it basic? We're starting with acidic. That one's a little bit simpler, so I know I have extra protons. Now, for this problem, we're told in the title that it's acidic. Sometimes you're going to be told it's acidic. Sometimes you need to figure it out. Maybe they already added H+, or you're balancing it in the presence of sulfuric acid. So you'd have to use a little bit of detective work to see if there's already excess H+ or hydroxide there. So hydrogen, 0 on the left, 4 times 2 on the right. I need to add 8 hydrogens to the left. We're in acidic solution, so I can simply add 8 protons. Over here, 0 hydrogens on the left, 0 hydrogens on the right. Don't break a good thing. It's already balanced. So then we can balance our electrons. I need to see the total charges that I have on the left-hand side. I have 8 plus charges and 1 negative charge on the left. So that gives me a total of +7. On the right-hand side, I have a total of +2. I can only add electrons. So which side do I need to add electrons to balance the charge? We're going to put this to a vote. Do I need to add electrons to the left or add electrons to the right? We're going to go by show of hands. Who says add them to the right? Add electrons over here. Who says add electrons over here on the left? And that is correct. We can only bring that charge down by adding electrons. The difference between 7 and 2 is 5. So I need to add 5 electrons. So now I'm going to go to my other half equation. Total charge of -2, a total charge of 0. I can only add electrons. I'm going to add 2 electrons to the product side to balance out the charge. Now, another little step to do here is we can double check. 1/2 reaction is using electrons, 1/2 half reaction is producing electrons. That's how it needs to be. One is using them, one is producing them. So we've balanced the electrons. Now we need to bring these reactions back together. If I bring them back together the way they are, I require 5 electrons and I produce 2 electrons. That's not going to happen for very long, well, at all, because it doesn't balance. We need to be producing and using the same number of electrons. So I have 5 electrons and 2 electrons. I somehow need to get one side or both sides to equal the same number of electrons. The way to do that is to find the lowest common factor. Well, 5 and 2, well, the best thing I've got is 10. I can't turn my 2 into a 5 or my 5 into a 2. The simplest thing is to multiply them. So I'm going to take this entire half reaction, multiply it by 2, this entire reaction, multiply it by 5, and then combine them. To make this explicit, I'm going to rewrite the equation and then combine them. And then we double check and make sure that we didn't miswrite a number. This is where it's really easy to make a typo. I want to make sure we have all our positive and negative signs and our coefficients. I'm now ready to add these up. I require 10 electrons. I produce 10 electrons. I can factor those pieces out. I don't see anything else that can factor out, so I'm going to rewrite my balanced equation. Yes. So that's how easy it is to make a typo when you're rewriting something. So we always want to pause and double check and double count. And then a nice way to check to make sure that it's correct is to count up. We have 10 carbons, 10 carbons, 2 manganese, 2 manganese. Overall, the charge on this side is 2 times plus 2, which is plus 4. Overall on this side, negative 10 minus 10, which is minus 12, plus 16, which gets me to plus 4. Super. We have double checked, and it matches. Before we wrap up, we have one more important thing to talk about. The next example is going to be on OWL, because the basic equation that we're going to balance is a disproportionation reaction. So rather than balancing something in base and then a disproportionation in base, we're going to see what this disproportionation is. It's possible to balance a reaction and to have a redox equation where the same reactant is both oxidized and reduced. Hold tight for one more minute and we will still wrap up early. If we have a species that can have more than one stable oxidation number, a lot of the elements in our periodic table, especially in the transition metals, can have more than one stable oxidation number. Iron could be plus 3, it could be plus 2, and it could be 0. Copper could be plus 1, it could be plus 2, it could be 0. It's possible to have a reaction where there's only one reactant, but there are 2 products, where the copper is both oxidized and reduced. How is that possible? Well, we don't just have one atom of copper. We have millions of copper plus ions. Some of those millions are oxidized, some of those millions are reduced. When we come back our next class, we're going to balance this disproportionation reaction. Have a great day.